Hi friends, how are you? Welcome to the lab session 4 on string operations. This lab session is going to be very interesting, and I hope that you have watched all the previous lab sessions because this will make clear sense in terms of the flow of our discussion and in terms of how we use an ALP to do something practical. All right, so let's begin our discussion on string operations. Before we actually write some ALP regarding strings, I first of all want to cover certain basic instructions. So here I have compiled instructions for you. And so the first category is of the repeat instruction. So this will repeat an instruction. This will repeat an instruction for a specific number of times, or as long as the condition is met. So like you can see in the explanation, repeat the given instruction till cx is not equal to 0. Repeat the given instruction while cx is equal to 0. Similarly, you have for zero flag and repeat not equal to, and repeat the given instruction while zero flow is equal to 0. So this has been covered deeply, I think, in the lectures. So go ahead, revisit your lectures, watch the lecture slides, and this will make more clear to you how to use them. All right, then we have the move SB, move SW, move SD. So every operation, move S operation, will have many of these operations which you'll see later on also, like load, store, compare, or scan. Each of them have a similar flavor of either doing it for 8 bits or for 16 bits or for 32 bits. So that depends on the kind of problem statement you are attempting. So you just have to be attentive that which instruction will be most suitable for your problem statement. All right. So here the move does a very simple operation by uh, moving the contents from ds colon si into es colon di from your stack, from your source index to your destination index. All right. Next we have the move day. Okay. All right. So I think I had covered this before, right? So this is just repeated. So load. Just a second. What? Hmm. So load SB, load SW. I'll probably edit this out if I get time. So load SB, load SW, and load SD are doing something similar. So it moves the byte at address pointed by SI into the AL register. If it is 16-bit, it moves into the AX register, and if it is 32-bit, it moves into EAX register. And depending on the operation, it moves the source index by that much amount. All right. So if you just do a repeat operation, so it will keep on increasing it and keep on storing it. So uh, storing it into the register. Similarly, you have the store operations, which does now picks up from the destination index and picks picks up the content from the register and moves it to the memory, external memory. All right. So here, if it is your microprocessor, here is your ALP. All right, operands coming in, and here is your register internal, and your memory is lying somewhere outside, right? So it will pick up this store instructions, will pick up the content from the register and move it to a memory location and will increase the source index appropriately. All right, so this is another flavor. Then we have the scan and the compare. Now I think these two are most important ones, so let's understand them theoretically and then let's understand them with a follow along example. So it compares the byte pointed by this destination index with AL and sets flags according to result. So internally what it does is a subtraction operation of both, and it sets some flags based on that. All right. So this is what scan does. And what compare does is that compares the byte at destination index with the byte at source index. So if two memory locations are being compared, then we use the compare operation. And if the destination is being compared with something stored in your register, then it's a scan operation. All right. Now both of these things are independently used. Like you can sometimes instead of scan, you can make use of compare. But in certain algorithms, you'll see using scan will be much more easier than using compare or vice versa. All right. So let's start with a follow along example. Um, Write an ALP to find the first occurrence of character in a string of characters and store the index in memory location res. All right. So what you have to do is that if there is a string given to you, string of characters. So let's say 12h, 34h. So this is 0, 0th index, first, second, third, fourth, fifth. And then in your AL register, if you store something, let's say 42h, then what do I want is that uh, wherever this 42h occurs for the first time in the string, that index you store in my result. All right. So now pause the video, try to solve this on your own based on what we have discussed so far. All right, so let's begin first of all by opening our DOS box, mount d colon masum 611 bin. All right, and quickly let's check whether debug x is working or not. It's debug x, not debug x. So it's working. Uh, let's open our VS Code. All right, and let's type this out. All right, I'll copy the initial part of the code. So this is what we have been given with, right? Obviously, the next step is dot code dot startup dot startup. So first operation which we have to do is let's check this. What does the slide say? Which byte do you want to replace? Store that in AL. And what is the length of the string? Store that in CX. And which string operation is most efficient to use in this? Um, that we'll answer next. All right. So don't look at this part. Okay. So as of now, we'll do these three operations: move, AL. Actually, I have them already with me, so it'll be quick if I just copy this along. So move AL, CX, and move AL 42H. So this is the byte which we want to search, and CX is the loop counter, which will automatically get decremented each time we're trying to search. And then we have the di my string, which is the destination index, which is pointing to the start of the string which we have here. All right, so the next thing is obviously the loop. So just think about it that if I let me write it here as well, let me point to a new memory location, search loop, and we'll go on repeating certain instructions till the time we're able to find the first occurrence of that. All right, so what scan is we will do is that it will compare. So let me take out my pen for a minute. All right, so at the time when this is getting executed, what we have, what will actually get checked is the AL byte. So the the byte which is stored at my AL register, and this will be compared to the memory location which is pointed by di. All right, so these two things will be compared, and based on that I can make a decision whether I have to jump, like because this operation will set certain flags, and based on that I can make a decision like if they are matching, what to do. If they're not matching, then what to do. All right, so the basic structure will look the same. So if I have a search loop, I'll scan for it. If I found it, that means if both of them are equal, if the compared bytes are equal, so the zero flag will be set, and I can go to a new memory location which I'm calling as found. If it is not, then I would certainly want to again loop back to my search loop, capital loop, search loop, and what this loop operation will do is that it will automatically decrement the counter register. So either we can decrement it and then use the statement jump to jump back, or we can manually do that. But here is an efficient way of doing that because it automatically decrements the count for you. So just this new keyword, remember that. And now if this whole operation is completed and we haven't found anything, then what we have to do is we have to jump to memory location which is we're calling not found. Okay, that means I'll have to define a new memory location called found and not found. So if I have found the instruction, then I need to store that into the results. All right, so which is going to be the next part in our slides. What if we found the character? So here, look at it properly, that right now, if this was my memory location, so di started from this point. Let's just quickly check what are the memories which you have. So here we have 12, 34, 56, 42, 34, 56, 42, and then we have 78, 9a. All right, so each time the scan is called, it automatically increments the di. All right, so so at this point when we have 42, we'll do a dry run and then this will make more sense to you. But understand this theoretically, that as soon as scan is called on this 42, so it will result of setting of the zero flag as 1, which means that now the loop will come out and will go to the found part. But at the same time when this instruction was getting executed, my di was incremented. So it is now pointing to 78. So if this is my 0th index, 1, 2, 3, 4, 5, the index number which I want is 3. And where the di is pointing to right now is at 78. Okay. So first thing which I'll do is I'll subtract. So this is actually having the absolute address right now. This is absolute in the sense segment colon offset format. And if I subtract from that the base of my string, I'll get this number. All right, I'll get this number. So this is what this first instruction is doing, that it is subtracting from di this offset of my string, and what you'll get stored in the subtract after execution of this is 04, and that you move into the bx register. So bx, and then you decrement the bx so that it actually points out to this index, and you load the effective address of the memory location to source index, and you do this move operation. Simply move si, the memory location pointed by si, and what you move into that location, your bx. Okay, so uh, and what if we did not find the character? So handle the case where the byte was not found in the string. So this is like up to your imagination, not imagination as such, but up to the requirement of your problem statement, that if you did not find, then based on that do you have to make any separate decision or not. So this is a typical flow. Let me complete this found and not found by. So here is the complete code where dot exit and dot end. Okay, So found, the same things which we did there, and not found. Handle the case where the byte was not found in the string. So just, you have to understand this fact that it will keep on executing sequentially. You remember your switch case in C? Like if you do not type a break after each of the case, then all the subsequent cases will get executed. So something similar here. Like if you want that now my program flow should not execute this part, so in C code you handle that by braces. Like in if else conditions you put braces, and that it's very easy for you. Here you just have to structure it in this way that if it is found, then do this, and if it is not found, then do this. Okay, and as long as this condition is you can go on for looping whatever is inside that condition which you have here. All right, let's I have it saved with me, so let me open a.asm. So this is the code. By the way, all these codes are available on the GitHub, so feel free to check out. I'll show you the link in towards the end of the video. Let me do that right now. So you can go to my GitHub profile, and you can click here to this and change from master to week 4. So there you will find all these codes written for you to directly execute, and if you're making any syntax error or something, so this will be little helpful. Try to type on your own. It will give you much more clarity. All right, and don't forget to star mark this repo. It will just increase my stats. So here you can star the repo. All right. Thank you for doing that. If you haven't, still pause the video and do that first. Okay. Now, let's execute this in our X compiler. Okay, so here we go. mla.asm. It's clean. Although when I was typing it first, I had to do multiple iterations just to figure out certain things. It's not always that easy to have a clean compile, so I always recommend that keep on compiling small pieces of your code as you're building up your ALP, so that towards the end you don't feel disheartened that nothing is working. Where have I made a mistake in my code? So sequentially keep on running the compiler just to check whether you're not making any syntax error or something, or using some wrong formatting of move operations, like an invalid instruction, as you got in your one of the quizzes. One of the problems was there based on that. To debug x and a.com. First thing first, we have to check which all instructions are we having here. So 0122, 0122. So 0122 definitely is pointing to the my string, the first part of my string, and the result where I'm storing SI somewhere down SI 0129. All right, so let me just note them down. Let me note down these numbers somewhere. Um, 0122 is where my string is pointing to my string. Let's check that memory location once, whether our data has got transferred properly or not. So 0122. Okay, so I see 12, 34, 56, 42, 78, 9A. And interestingly, I see 06. And then I see how many bytes? 2 bytes, a DW. Since I'd given my result a DW, therefore 2 bytes are having some null value. I've initialized them as 00. After that, it's garbage. Okay, so we want actually to store this 42 in AL, and this will keep on checking, and if we find the byte matching, then we want to store that here. Okay, so let's keep on executing these instructions step by step. So the first trace is you can see that it executes this operation. So EL42, I have that. If I keep on pressing enter, then it will sequentially keep on executing trace only. If I would just press enter, then whatever was the last instruction that will get executed. So move CX 0006, and the next instruction is load effective address of DI. And now the interesting part starts. So you have to, I'll keep this code also with us, open side by side. Okay. So here we are right now. So what do you think? If I execute this, what will be the next instruction which will be executed? Obviously, this will be the case. Okay. Because here it's not doing any jump instruction. So if I execute this, it will still look for JZ. But now, depending on the condition, whether it found or not, it will either jump to this memory location or it will go for the next loop operation. Oops, sorry. Mm. So you see that it went for the loop operation. That means 42 is not in the first index. All right, let's keep on doing that. Scan SB, JZ, loop W. So neither in the second nor in the third. Now it's the fourth time. Now the DI is actually pointing to the memory location 42. So if I do a scan operation, my 0 bit is set. My 0 bit is set. So you can see that NZ has changed to ZR. And if I do this now, then it will jump to the subtract instruction. So let's see that. Yes, it works. It works. So now based on this, in my DI location, which is now pointing to the absolute memory location 0126. See this, it's now absolute I'm calling, where exactly in the memory location it is pointing to. I'll try to take the difference between that and the offset. So 0126 and I subtract that, so it leaves me with 0004, as we have discussed in the theory why it has happened exactly, right? And that I'll move to the BX. So the BX has the value 004 now, and I decrement my BX to exactly point out the address of 42, and I move that into my SI, the memory location pointed by SI. So all I have to do is again go back to D0122, and there you go. You see 0003 stored in Little Endian. Whatever is stored in the register, it's not Little Endian. Whatever gets stored in the memory, that is Little Endian. All right, that is a very important thing. Many of you have made this mistake in quiz. Whatever you're storing in register, also that you're storing in Little Endian format. No, that is not how it works. Okay, but another simple way to do this without all this clutter of uh, looping and everything is by using this operation of repeat statement. So here this format is something like this, that keep on repeating this instruction as long as this any does not uh, you know it is not equal to. So let me explain you in this way. So I'm referring to the lab manual which we have uploaded, and you keep on going down. There you will find a section on this. So what is rep any and rep instruction? Rep any is repeat not equal, and rep is repeat equal. A prefix instructions in the x86 assembly language used to repeat string operations with certain conditions. So repeat any prefix is used to repeat a string operation as long as the condition for not being equal is met. It can be used with string operations such as scan SB, compare SB, scan SW, compare SW, basically all the instructions. So it will keep on comparing, and if the both the things are matching, then it will simply exit out. So repeat as long as they are not equal to, and as soon as they become equal, just stop doing that. So here I have taken another example of 01 010203, all these are there, and what I have stored in my AL is 07H. All right, so This is try executing this problem. I have this with me, so I'll simply paste this and show you the execution of this. It's in the b.asm file. Okay, and this, let's actually run it and see. By the way, CLD, you have to you should probably do it in the initial thing also. Do not depend that always that direction flag will be 0 and it's going upwards. So that is one correction which you have to make in the previous problem. That luckily we got our direction bit set as 0, so it was going upwards, but explicitly define the direction flag. All right. So I'm storing in CX the count. I'm storing in CX the count, and in AL I'm storing what I have to compare. Okay. And I'll keep on repeating this scan SB as long as they are not equal. So it will go on comparing, and as soon as it is equal, it will escape. And if it escapes at that time, the DI will be pointing to the uh, memory location which is in front of that where the match happened. So this part of the code is exactly the same as what we saw in the previous, just to store that uh, value into the result section, the calculation of the index, and just this top part has got reduced. So you see how much the complexity has reduced from going from a.asm this code to this code. All right. So using these instructions will make your life easier as well as our life easier while checking. We don't have to individually go and understand, because understanding ASM, writing ASM is one thing, and understanding ASM, your ASM seeing your ALP is another thing. Okay, so let's save this and go to the DOS box and let me compile this. Oh, I compiled a.asm. Let me compile code1.asm dot exit, and very important. Okay, and now debug x code1.com u. So load effective address, move all these things, see it sequentially. So let's check out the memory location first. Very important to do that every time. 0128. Remember this 0128. I'll note this down somewhere. 0128. Okay. Oh, sorry, this is the result. Okay, I want to check the array one. So which is 011A. Let me note that down as well. 011E. Was that right? 011E. Yes. So DS 011E. Okay, chill. ALP is not wrong. Like this whatever you type, this works basically. So 010203, all this. Let's see what is the next instruction to be executed. So let's do it sequentially. I'm just figuring out the memory location of my result, then storing my DI as in my DI, the starting of this array. Next step is move AL07, which is the byte which I want to compare. And then CX, I'm typing in the maximum length of the string. Note that I can type here 10 as well because they're just 10 operations, but it's better always to not intermix your decimal and hexadecimal. Like stick to just one. Okay, it will make your life, it will make your ALP much more easier to you know code, understand, debug everything. So even though it seems easier to just type 10 here, still convert it into hex. Whatever you do in microprocessor, keep it in hex. Take it as a golden rule. This reminds me that there are certain offenses which are left, so I'll probably cover them very soon, because now is a good time that you'll be able to understand and appreciate those offenses. So as long as you keep on following those pointers, you will not make a mistake in your ALP, writing of ALP. Okay. So CX, you can see that value has got stored. The next instruction is setting up the direction flag. All right, so it was already 0, therefore no change you can observe here in the direction, in the flag bits. By the way, I forgot which one is the flag bit, so don't, I can just check it online. Okay. Now is the interesting instruction. So if I just press one single enter, this repeat, like in the loop operation, you could see it going back every time. Now this entire thing will be, condensed. It's just like a one single instruction from user's perspective. The microprocessor will keep on doing this operation without you giving it any external, command. It will keep on executing until it finds the condition where the repeat, where this, they are not matching. So it will keep on repeating as long as they're not equal to. As soon as they become equal, it will just break. Okay. So I just have to press a single enter, and there you go. My DI, which was pointing to 011E, is now pointing to 0125, which is the 08. Okay. You do not trust me. So let's see 0125. And you can see that it is the 08, which is it is pointing to. Okay, so this works. You just have to understand that, how it is coded. Now the next operations are fairly straightforward of how I want to move that thing into my result section. So if I again do a day, this time on 01, let's type 011A. So after this, you'll see that it will be the 0006, which is the index of this 07 byte. Okay, so quickly moving forward, time is already almost half an hour. So if you have understood this much, then compare will also be very easy for you to understand. Write in ALP to compare two strings and store the index where the two strings mismatch in memory location. Where store the index where the two strings mismatch in a memory location pointed by res. All right. So at this point, you want to store this memory location, the index of this, where these two things are not matching to the memory location res. So try on your own. Think which string operation would best work in this situation, because now you have two memory locations. So obviously I've given you enough hints, but do pause the video and try attempting the problem on your own. All right. So did you figure it out? Compare SB would work the best. What is the string size? We have to store that in CX. So in my case, unvovalence, it's how much? 14, right? So 14, I'll simply store 0D, not 14, 0DH. And I'll clear the direction flag. And it's a very simple operation now. I'll keep on, as long as they are equal, I'll keep on. In the last operation, what I was doing, if they were not equal, I was moving forward. Here, the statement, the requirement of the problem is, as long as they are equal, I need to keep moving forward. The algorithm itself says so. So as soon as the two bytes do not meet each other, so SI and DI, they're pointing to the individual strings, right? I don't even need to write this actually. It's so simple to understand that you can understand just like that. That SI is pointing to that one, DI is pointing to that two, and my that one and that two are my names. Only the small e and capital E are different, and that is something, you know. Uh, it's not case sensitive obviously, because small e and capital E have different representations in hex. So I'll keep on doing this operation, and whenever they meet, that is the location where, things are not matching, and I have to break from that point. So how to calculate the index where the mismatch has happened? My SI would be pointing at the time of mismatch. So if this is Anubhav, L hence, and here it is Anubhav, L hence with capital E. So SI at the point where this breaks, SI will be pointing here and DI will be pointing here. Okay. So either I do, to calculate, what I do, I subtract the offset of that two, because that two is pointing here and that one is pointing here. So if I subtract these two, then I'll get out this difference. If I subtract SI from offset of that one, then I'll get out this difference. So you just have to keep this thing clear based on your requirement of the problem. Either of these things can be asked. Okay, keep a note of that. How to calculate the index where the mismatch happens? So this is directly from the previous question. Okay, so now go ahead and let me show you the execution very quickly of this in my code. When I'll copy my code, so everything what you see here is like, first I wrote this, then I copied this in there. So obviously this is not wrong. I'll save it. I'm just showing you the dry execution, because writing ELP is one thing, but just seeing how it works in MASM and debugX is another thing. So therefore I feel that it is important that we go to DOSBox and type every question and see the execution, not just discuss theoretically, because theoretical discussions are anyways happening in the lecture class. So here it's more like a practical lab problem, so therefore it's better that we type it. So ML code one might already be the code1.asm and debugx code1.asm. So here you see that that one, that two are getting loaded, so I'll just note them down: 0120, 0120, and we have 012e. Okay, so the first thing is that I would definitely, let me keep this code side by side. So one thing definitely which I would love to do is, first of all, go to memory location 0120. There I see Anubhav Elhens and Anubhav with a capital E Elhens. Okay, and next thing is checking the instructions. So first I executed stored in the SI my dat1, stored in DI my dat2, then move the complete, how much is the length of the string in CX, and cleared the direction flag. And now just by executing one single instruction, it will, without even telling you to loop back, decrement everything, it will just stop at that point where the mismatch happens. So this is what amazing, the repeat, this is the power of repeat A. And in the previous example there was repeat any. So it's just, if you learn to use these two instructions, you'll be so much quicker than majority of the people who are writing the exam, and your ALP size will be much smaller and it will be correct as compared to those who are making all the loops. So do not forget to, use these instructions wherever they are relevant. Okay, so let me execute this. Enough of talking. Okay, so just note that where my SI is pointing to and where my DI is pointing to, 0128 and 0136. Don't trust me that it is pointing to the maximum location. Try seeing it for yourself. 0128. See, it's pointing to small l, SI, and D 0136. Sorry, 0136. 0136. It looks almost the same, but it is the next one. It is this L which it is pointing to. Okay, so this works. These instruction works. Right now, it might be very obvious that why is even sir showing this. And I'm so smart. Like we can understand this, but if you do not appreciate such small points, then you cannot write down in your paper or exam. Okay, you need to learn how to appreciate such small points, and you need to learn how to check them in MASM or debugX. Okay, then. um the rest of the part is, I think, very straightforward. We have already tested out, so no need to go into that. Head over to your lab manual and check out the lab problems which are there. Click on more pages and you'll find your lab tasks there. You have a starter code available with you, so you can directly download it and can start filling in your code. Okay, that is it. Thank you so much. See you again next week.